You also need to have a table for cubes. So you need to have a table for perfect cubes. Again, you need numerical and you need literal. Well, for numerical, for cubes, we start with 2 times 2 times 2. Well, 2 times 2 times 2 is 8. So 8 is a perfect numerical cube. Then I do 3 times 3 times 3. 3 times 3 is 9. 9 times 3 is 27. So 27 is a numerical cube. I do 4 times 4 times 4, which is 64. 64 is a numerical cube. I do 5 times 5 times 5 to get 125. 125 is a numerical cube. I believe I'll stop with that and just put dot, dot, dot. You see the pattern, so you can make as many as you need. To do the literal, I would do a cubed times a cubed times, well, let's start with a. I don't know, a to the first times a to the first times a to the first. And that would give me a cubed. Because multiply powers having the same base, I keep the base a and add the exponents. 1 plus 1 is 2 plus 1 is 3. Then I could do a squared times a squared times a squared. That would give me a to the 6th. Multiply powers having the same base, keep the base, add the exponents. 2 plus 2 is 4, 4 plus 2 is 6. Then I could do a cubed times a cubed times a cubed, which gives me a to the 9th. 3 plus 3 is 6. 6 plus 3 is 9. The next would be a to the 12th, because notice the pattern, 3, 6, 9, 12, then 15, and so forth. And in other words, for cubes, the exponents are multiples of 3. So you've got your numerical cubes, you've got your literal cubes. I'm going to force, and if you have fifths or sixths, you need to make your own. Okay, for force, for numerical, I do 2 times 2 times 2 times 2. 2 times 2 is 4, 4 times 2 is 8, 8 times 2 is 16. So 16 is a numerical fourth. Then I can do 3 times 3 times 3 times 3, which is 81. 3 times 3 is 9, 9 times 3 is 27, 27 times 3 is 81. Then I can do 4 times 4 times 4 times 4. And 4 times 4 is 16. 16 times 4 is 64. 64 times 4 is 256. So 256 is a numerical cubed. We'll do one more. 5 times 5 times 5 times 5. 5 times 5 is 25. 25 times 5 is 125. 125 times 5 is 625. So 625 is numerical fourth power. And I'll put the dot, dot, dot to say that show that it continues. Now we need to do the literal force. So I do A times A times A times A. Well, I've used A as a factor 4 times, so I would have A to the 4th. Then I can do A squared times A squared times A squared times A squared. That would be A to the 2 plus 2 is 4, 4 plus 2 is 6, 6 plus 2 is 8. Well, it's going to be, exponents be multiples of 4, since we're doing fourth powers. So it'll be A to the 4th, A to the 8th, A to the 12th, A to the 16th, and so forth. So you need to be familiar with perfect squares, perfect cubes, perfect fourths. You need to be able to make the table for any perfect power that you should need. Okay, let's look at an example, and let's simplify the cube root of 81 x to the 4th. We want to simplify the cube root of 81 x to the 4th. So what I want to do is to factor it into the cube, since I have the cube root and what's left. Well, what are your cubes? Is 81 a cube? Well, I'm going to pull the cubes back, and we need to find a cube that will go into 81. Now we're looking at numerical cubes. 8 will not go into 81, but 27 will. 27 goes into 81 3 times. So I can write 81 as 27 times 3. Whereas 27 is your cube, the 3 is what's left. And be sure to put my cube root in. So the perfect cube is 27. The 3 is what's left. And check yourself to make sure that 27 times 3 is 81. Now we have x to the 4th. Again, you look at your cube list and you see that a to the 4th is not listed, but a cubed is. So what I can do is I can put x cubed here and x over there. Now you can always check yourself at this step by asking yourself 2 questions. Is this a perfect cubed? Well, 27 is in the cube list. X cubed is in the cube list. So 27x cubed is a perfect cube. The second question, if you multiply 27x cubed times 3x, we get 81x to the 4th. Well, 27 times 3 is 81. X cubed times x is x to the 4th. If you get yes to both of those questions, you know that you're correct to this point. All that's left is to evaluate the cube root. The cube root of 27 is 3. The cube root of x to the cubed is x. Now remember, all you need to do is to divide the 3 into 3, which would be 1, so it's x to the 1st. Now that's, you can divide the index into the exponent. You have to do the cube root of 27 by saying what uses a factor of 3 times gives 27. You can do the same with x. What uses a factor of 3 times gives x cubed. So it would be x, since x times x times x is x cubed. So when I take the cube root of 27x cubed, I get 3x. And then I just have to bring down the what's left. So I have 3x times the cube root of 3x as the answer. Let's look at another example. Let's simplify the square root of 98, x to the 6th, y to the 7th, z to the 9th. Well, I need to break this into the square root of perfect squares times the square root of what's left. That's how you always break it down. Well, in order to get the perfect squares, I need to go back and look at my list. I need to pull out squares. Now what about the perfect squares? I need to find something that will go into 98. You can take your calculator and you can start dividing. You can divide 4 into 98. It won't be even. You can divide 9 into 98, 16, 25, 36, and finally you come to 49. 49 will go into 98 2 times. So I can write 98 as 49 times 2. Now we have x to the 6th. Well, notice that a to the 6th is in my list of squares. So x to the 6th is a square. Now I have y to the 7th. Okay. Y to the 7th, or a to the 7th, is not in this, but a to the 6th is. So I can write it as y to the 6th times y. Notice you want to take the very largest square that you can. Now as far as y to the 7th, I could have said it would be y squared times y to the 5th. But y to the 5th would still have another perfect square as a factor. So what I need to do is to take the biggest of these that will divide into it. And the biggest of these squares that would divide into y to the 7th is y to the 6th. So I can write y to the 7th as y to the 6th times y. Now z to the 9th. I'm going to give you a moment to think about which of these perfect squares I need to use to factor z to the 9th.